Alright, let's go ahead and solve another question. It's kind of important. So here's what the question statement says. So we have to read the question very carefully. 15 horsepower. Okay, immediately you think that this is going to be in British gravitational. It's not going to be in SI. Good, we are practicing for it. Okay, this is centrifugal pump. It's a type of a pump that we are going to study in fluid mechanics, not thermodynamics. With 90% efficiency. So the efficiency of the centrifugal pump is given to me. And this is used to pump water from a nearby water container to a storage tank. So I'm picking up some water from a water reservoir and pumping it to a storage tank. If the flow rate is 1 feet cube per second, that's given to me, and the free surface of the storage tank is 100 foot above the water reservoir, determine the amount of mechanical power lost to viscous effects in the pipes. This also can be said as friction in the pipes, but I don't like that terminology because friction doesn't exist for fluids, it is for solids, okay? But if you look at different references, sometimes they call this friction. Anyways, that's a side point. So these are some of the options, okay? As I always say, please stop the video. Do not watch this like a Netflix. Go ahead and do this on your own. Come back and check whether you can do it. So let me first draw what I'm talking about. So I have like a water reservoir. It's gonna be a pretty bad drawing, but I think it's gonna do just fine. Okay, and over here, this water reservoir, and I have another water storage tank over here. Okay, and what it says is I have a pump that is connecting these two. The pumps are like this, maybe. Okay, something like that. Doesn't have to be that accurate, right? So this is the pump. It's pumping the fluid from this container, it says reservoir, to the storage tank. Okay, so alright, and it says that this particular pump has 15 horsepower, that's the power of it, and is 90% efficient. I want to talk for 1 second about, is this an unrealistic number, 90%? Well, like if the pump power is about over 10 horsepower, it can go up to 93% or 95%. So this is fairly realistic, okay? So this exists in real life. All right, that was a side item. So then let's get to business, right? The first thing I want to do here is let's analyze this particular pump, right? This pump says that it is 15 horsepower, but then it is 90% efficient. So what it means is I'm going to input that 15 horsepower, and the output of that will be 90% of that 15 horsepower. So what is it? 13.5, right? Horsepower. That will go into the pumping of the fluid. That's the main goal of a pump, right? It's the pumping. All right. So that is something. Now I know. So I have a total of 13.5 horsepower, and you can see all these numbers over here is much lower than this. This makes sense. So all right, fine. Here's the thing. What I want to do here is to see actually how much of this power goes to take a fluid, let's say it was here, and then suck it over here, continue through here, and just go into there. Okay, let's say point 1 to point 2. Okay, actually this I forgot to tell you, but well, I didn't forget, but this is 100 foot that is given in the question statement. Okay, so let's look at this energy change of this particular, it's called a streamline. Okay, but let's take a look at this streamline going from 1 to 2. Okay, so let's look at delta E of that particular 1 to 2, or you can call this fluid as well, because that's the only fluid that I'm dealing with over here. If you watch my lecture videos, you will see that this is going to be m dot times delta E. Okay, where delta E is defined for a simple compressible substance such as this is going to be Gz plus the internal energy. Okay, so let's look at each of these components. So the velocity. So the thing is, this is a per 1 kilogram, so this is a reservoir, it's huge. Just removing 1 kilogram doesn't really change the velocity going up or down of this level, and same argument can be made for this as well. So there is no velocity over here, so the velocity will be 0. Okay, so both cases, so this is gone. Gz is going to be there because I gave you the height difference, right, for sure. How about the internal energy? We'll talk this more about in module 3, but you know already that the internal energy, or more specific internal energy, depends on the temperature, pressure, so state postulate determines that I need two properties to define my system. So you can see here, just because of it goes from here to here, there will be no significant pressure change because it's open to atmosphere. This is open to atmosphere, and I don't anticipate the temperature to go up, significantly. It may go up slightly, but not so. The U can be taken as a constant as well. Okay, so as I'm looking at the change, I'm not saying U is 0. I'm looking at the change of it. The change of it is not going to be there. Okay, so this is delta. Okay, so far so good. So what I get is delta means that this is going to be basically m dot g z. Z is the height difference with basically 100 foot for this particular case. Okay. So one thing I want to note is that the flow rate is 1 feet cube per second. So the flow rate that is given to me is 1 feet cube per second. Is this m dot what I gave you? No, this is actually volumetric flow rate. Okay, we discussed this previously as well. And the relationship between the mass flow rate and volumetric flow rate is by multiplying it by the density. Okay, let's not forget this, dot at the top. Okay, so then I'm just gonna simply go ahead and replace this here, right? So then, so far it's gonna be rho g volumetric flow rate times the z. That will be the energy change at the end of the day by the existence of a pump. How much of the energy of the system has changed over this distance that we are traveling from 1 to 2. Okay. Now I have all these, so I can simply go ahead and plug this into my calculator. But let's first write it. So the first thing is density. So the density of fluid in the British gravitational units is going to be this, pound feet cube. Okay, 62.4 pound mass divided by feet cube. This is the unit of mass. This is the unit of volume, m over v. So far so good. Let's continue. What is the gravity? You should know this, 32.2 feet per second square. Okay. What about the volumetric flow rate? Well, I gave you what? It's going to be 1 feet cube per second. Let's not forget the z. The z difference is 100 foot. Okay, so let me actually punch this into my calculator. I'll be right back. Okay, I get this to be 200,928. Okay, so let's just simply multiply them and see, like feet cubes will cancel over here, and I will get a pound mass times, let's see, feet square, right? So because I have a feet here, I have a feet here, and how about the denominator? I will have a second cube, right? Second cube. Okay, so here's the problem. This is fine. There's nothing wrong with this, but I did not give you, or at least I do not know the conversion of this unit into the horsepower. Okay, I know the conversion from pound force, so I need to convert this to pound force. And if you look at my video, I think 1.2, you will see that 1 pound force is equal to 32.2 pound mass times feet per second square, right? So I simply want to do that substitution over here. So what happens is, you can see now I have to divide. So I'm doing very detailed over here. You don't actually have to divide multiply by this. You can take a shortcut. I'm doing the long cut. Okay. So you can see I'm gonna now divide this by 32.2, and that will be. Just give me 1 second. Okay, I'm back. It is 6,240 pound force times. Now let me see. See this pound mass. So this okay. Feet. So one of the feet are cancelled. Second square. So this becomes 1. So times feet per second. Do you see it? Okay. And now this is nice. It makes me smile because I know that 1 horsepower is equal to 550 pound force times feet per second. Okay. This makes sense because this is the unit of power. This is the unit of force times velocity. Force times velocity, right? Power. So okay, so everything seems good. So then I need to divide this by 6,240 by 550, and if I do it, I'll get the horsepower component as, give me a second, 11.34 horsepowers. Okay, so here's what's going on. So I have 13.5 out of 15 going into the fluid to pump the fluid. But not all of them are used to change the energy of the fluid. Only 11.34 horsepower of that does. So then, according to the question that's asking me, it's asking me what is the viscous forces, that is, or rather the power that is spent or wasted on the viscous forces. It's going to be the difference in those two numbers, the pump power minus the actual what is being delivered into the fluid. So you can see in here that it's going to be 13.5 horsepower minus 11.34 horsepower, and that will be what, 2.16, right? Something, yeah, 2.16 horsepower. So that will be the amount of power that's been spent over there. So you can see this is the option A is the right answer for this question. Thank you for watching this segment. I hope you understand this. This is on the higher end or difficult side of the spectrum. Okay? Have a nice day. Bye-bye.